Hello class, this is Mrs. Gallegos, and today's lecture will be on metallic bonding, topic 4, section 5, last one. So far we've learned how atoms are bonded in ionic and covalent compounds. So how are the atoms of a metal bonded? First of all, we know that all the metals have low electronegativities. They're on the left-hand side of the periodic table. So we know that each metal easily loses its valence electrons. And so if there's no nonmetal there to pick up this valence electron, what happens to it? And so what we see in metals is that it is a sea of metal ions surrounded by a sea of valence electrons. And so the force of attraction, and we know it's a very strong one, especially when we look at the physical property of melting, the attraction is between the metal ion and all of the electrons in the sea of electrons. And so it is said that metal bonds are formed between the nucleus of each of the metals and the delocalized electrons. So it's a giant lattice of cations and delocalized electrons, whereas the covalent bond, the electrons are localized between two atoms. In a metallic bond, the electrons are delocalized among all the cations. And so a metallic bond is similar to an ionic bond because you form this giant lattice, but it's not alternating negative and positive charges. It's just this lattice of cations with the surrounding delocalized clouds of electrons. So in this case, what determines the strength of a metal bond? And again, like the covalent bond, like the ionic bond, this has to do with the charge of the ion, not the charge of the electron, the charge of the ion and the ionic radius. And that goes back to Coulombic attraction. The force of attraction between two oppositely charged particles has to do with the magnitude of the charge and the distance. So if we look at beryllium, which is the very top of the alkaline earth metals, we see that it has a very large melting point, and that is because beryllium has the smallest ionic radius of, and if you look over to the right, it has the smallest ionic radius in the family. And then if we go to the bottom of the alkaline earth metals, where we have, well, almost the bottom, period 6, we have barium, whose melting point is 727, so it's lower. And then if we look, because the ionic radius of a barium atom is 134 picometers, which means that it is larger, almost 3 times as large as a beryllium ion. So that means that the ions are farther apart from each other. Now, if we were to compare, if you look at the diagram on the bottom, if we were to compare a group 1 metal to a group 2 metal, here we have the same, we have different charges, and so we have the magnitude of charge is greater, so we know the force of attraction would be greater. Not only that, but the group 2 metals ions are smaller in size. Because as we go from left to right in the periodic table, the ionic radius, the radius decreases, therefore the ionic radius decreases. And so the group 2 metals would have much higher melting and boiling points than the group 1 metals, the alkali metals. And so what determines the strength of a bond is the charge on the ion and the radius. And of course this is related to the number of valence electrons. So what are the physical properties of the metals? I think of all the elements, these are the physical properties most familiar to us. We know all metals conduct electricity, and that's because of the free-moving electrons. Just like an ionic substance has, when it's dissolved in water, the ions are able to move about, so they're moving charge, and so they'll conduct electricity when they're either liquid a liquid state or an aqueous state, but they won't conduct electricity in their solid state because there's no moving charges. Well, metals always have moving charges because that's how they're bonded together. So that sea of electrons allows metals to both be electrical and thermoconductors. And in the same line, metals are also malleable. Because if you think about it, because there is no localization of electrons, if I pound a metal, the nuclei will simply slide back each other. So if you see the picture on the bottom, if I stress by pounding a metal, because there's no localized concentration of electrons, the electrons will just move about, and so the nuclei can just pass by each other without snapping the metal. And because this is a very strong electrostatic attraction between the cations and the delocalized electrons, the metals have very high melting points. And then ductility means the ability to pull the metal into long wires, and that's related to its ability, the malleability of the metals. So those are the physical properties of the metals. So what is an alloy? Well, an alloy is a mixture of two or more metals, and on the right we have brass, which is a mixture of zinc and copper. And we see that the properties in an alloy are different than the properties of either pure metal. And one of the properties that an alloy provides the combination of the metals is that because you have, especially if you have two different sized metals or a metal and a non-metal in your alloy, as you can see, it prevents the metal from being malleable, and so they are much stronger, but then also more brittle.